Hello and welcome to this video. In this video you will learn how to use the stratification method of reducing the variance of your estimators when you're trying to estimate some parameter of interest. This could be the mean of some random variable. The variance of your estimators is incredibly important since it plays a huge factor when you try to build confidence intervals. So reducing this variance will help you a lot when trying to build precise estimators. The method I am going to teach you in this video is where we use so-called proportional allocation. This is a very easy and intuitive method, and hopefully I will do a good job of explaining this theory. I will first go through the theory while going through an example where the parameter of interest is the mean of a standard uniform random variable. Then in the end, I will implement the method in Python so you can see just how effective this relatively simple method can be. So yeah, let's get to it. Okay, so let's get started. Assume we have x, a random variable, and we wish to estimate the mean, which we will denote by mu. So that is the mean of x. And this guy is of course unknown. We wish to estimate it through some kind of simulation. And we could use crude Monte Carlo, where we simply simulate a large amount of x's, and then take our estimate. We had to be equal to 1 over r sum r I equals 1 of these xi's. And in a lot of cases this gives a very good estimate, but I want to see and show you a method where we can lower the variance of this estimate such that the bounds of our confidence intervals will be smaller. Okay, so how do we do this? We do this through, if it will let me go down here, through stratification. So the idea is, if omega denotes the sample space of x, then if our omega has some shape, let's say it looks like this, then we might want to partition this sample space into some smaller parts. So in this case, I split the sample space into 4 parts. And as you can see, these parts are not necessarily of equal size. And generally, if we say we split it up into k parts, then we call these parts stratas. And now, for this method to work, we assume that pk, which we define as the probability of x being in strata k, that this is known. I'm running out of space. This is known. Okay, now we define x, xk, which we set equal to x given x is inside omega k, or at least we say they have the same distribution. And we assume that we can simulate this type of random variable, and we set mu k equal to the mean of xk, which will then be the conditional mean of x given x is in omega k. Okay, now this might seem a bit abstract at first, but I will make an example which we will follow along with this theory. So an example could be that x is uniform 0.1. That means that omega is the interval between 0 and 1. Then we might, this is a bit arbitrary because this is just a toy example, but we might split this into omega 1 here from 0 to 0.2. Then we might set 1 here. So we have omega 3 on 2 and omega 3. Then in this case, P1 will be equal to 0.2 because this is a uniform distribution and this interval is 1/5 of the entire interval. Similarly, this will be equal to, well, this has length 0.7 and this has length 0.1. And in this case, we also know the mu's, but this is not necessary. But in this case, mu1 equals 0.1. That's the, well, generally a uniform has the endpoint minus the start point and then divided, no, the endpoint plus the start point and then divided by 2. So mu2 is equal to 0.2 plus 0.9 divided by 2, which will be 0.55, and mu3 will be equal to 0.05. That is wrong, 0.95. Okay, now that was just an example of how we can stratify. Now we continue with the theory. So using the law of total expectation, this does not really look like a T, that's better. We can see that the mean of x, we can write this as the sum of small k equals 1 up to large K or capital K, the mean of x given x in omega k, because this was a partition, multiplied by the probability of x being in omega k. But this is simply equal to k equals 1 up to k mu k multiplied by pk, where these were known. So we can build an estimate of the mean of x by somehow building an estimate of this. And just for fun, let's continue the example. In this case, we wish this mean, which is 0.5 in our standard uniform, that is the mean of our x. We wish this to be equal to the mean of the first strata multiplied by the probability plus the mean of the second strata, which we found to be 0.55 multiplied by 0.7, and then plus 0.95 multiplied by 0.1. Okay, this is all equal to, like this we can write as 1/50. This will be 385 over 1,000. Yeah. And then if we want this to have the same denominator, we can write that as 95 over 100, no, 1,000. Okay, so This will be 20 plus 385 plus 50 divided by 1,000, which is exactly 500 divided by 95. So 5 in there, and this gives 0.5. Okay, so that's just showing that, yeah, this is what we would expect, because the law of total expectation is a well-known result, which is extremely useful. Why can't I go out here? Okay, thank you. Now, we let R be the total amount of simulations we have available. Then we write R as R1 plus everything else up to R capital K. This is the amount of simulations of x1, and this is the amount of simulations of xk. So simulations within strata capital K. Okay, now we define rho k to be equal to rk divided by r. So the fraction of simulations within strata small k. Now we estimate the unknown mu k using crude Monte Carlo 1 over rk sum I equals 1 up to rk of our realization of these xk's, and I'll just denote it by an I. So this is the ith realization of this. Okay, now please let me go out here again. Okay, what the fuck? Okay, now I define we had stratification as the sum up to k equals 1 of mu k hat multiplied by the probability. So we simply plug in the estimate of mu k in this sum, which we got from the law of total expectation. Now, we don't know if this is a good estimate. We have some important questions. First of all, has the variance been reduced? And secondly, how do we choose these rho k's or r k's? How do we decide how many simulations we wish to perform within each strata? And well, to answer the first question, we can consider square root r multiplied by mu hat stratified minus mu. You might recognize this way of writing something from the central limit theorem. Sorry, but we can't use the CLT in this case because our mu hat stratified, it might be unbiased. It has mean mu, but this is not the average of identically distributed, like these entrances are not identically distributed and independent, so this is not the right form to use the CLT. But what we can do is we can write this as square root r sum large k equals 1 pk mu k, and then we can write this out using the law of total expectation. Then you can see that this becomes a sum, this becomes a sum, and we can write that as this, where there's a hat over this one, Okay, we can write this as 1 over square root r, sum k equals 1 up to large K of pk, and then we divide this by square root rk. We are allowed to do this as long as we remember to multiply by it again. And here, this is an expression which is of the type which is used in the central limit theorem. So this guy is approximately normal distributed 0.sigma squared k, where this is the variance sigma k squared equals the variance of xk. So this is equal to the variance of the conditional, this is the conditional variance of x. I can also write that the variance of x given x is inside omega k. Okay, for this to be true, we need rk to be large. Large. So we can, for example, say larger than 100 will usually be all right in most cases. Yeah, that's a bit of a simplification, but yeah, I don't want to say more about this. You can look into this yourselves. But now, well, this is then normally distributed, and we just multiply something, a constant here, multiply a constant, take the sum, but they're independent. So that means that this all of this expression will be approximately normal 0 point, and then the sum k equals 1. Then we have to square these factors, so r, then we just move this over here, r divided by rk, pk squared, and then sigma k squared. And this we call the variance stratified here. Okay, and this is only if all of these rk's are large enough. And this is very important. Okay, now I move over here. Now, that was the first question. How large was this variance? We can't really answer that yet because we still don't know these rk's or these sigma k's for that matter. But if we just think about how to allocate, how to choose these rk's, I will only touch on one method. There are a lot of methods. There's even a so-called optimal allocation, which is the best possible, but that requires us to know the sigma k's, so that is not feasible in most situations. But proportional allocation has a lot of advantages. It is intuitive, it is easy to implement, and it always improves the variance. The variance, it always makes sure that this stratified variance is less than or equal to the original, but it can't make it worse. Okay, now you might guess it from the name, but this proportional allocation simply means that we try to make the proportion of simulations within our strata K equal to the probability of X being in strata K. And this is ignoring rounding errors and assuming all RKs are large. So for example, larger than 100. And remember, this is equal to RK divided by R. So this is a method. Choosing this is a method of choosing how large RK should be. Okay? Now, if we make this proportional allocation, then we can consider the stratified variance. Well, this was equal to the expression, the sum of k equals 1 up to k of pk squared multiplied by r over rk sigma k squared. But we can rewrite this as the sum k equals 1 up to large K. Then we can see that this is rho k to the power of minus 1. And this, because of this equality, we can write as pk multiplied by rho k. And this was rho k minus 1, or to the power of minus 1, and then multiplied by sigma k squared. But these two guys cancel out, so this simply becomes k equals 1 up to k of pk multiplied by sigma k squared. This is the variance. This is a probability of being inside the strata. So we can rewrite this as the expectation of the variance of X given some strata indicator where I is equal to 1 up to k with probabilities p1 up to pk, determining which strata X should be in. Or probably a better way of writing this would be omega I, or even X being inside omega I, so this is the expectation of the variance of X given X is inside strata I, where I is determined with these probabilities. And, well, we can write the actual variance, or the crude Monte Carlo variance. We write this as the variance of X which, using the law of total variance, is equal to the expectation of the variance of X given I plus the variance of the expectation of X given, and it's not given I, it's given this, sorry. And we can see that this is a variance, so this is larger than or equal to 0, and this is equal to the stratified variance. So this must be larger than or equal to the stratified variance, and there is only equality if this term is 0. So if this expectation is 0 for all outcomes of the I. I don't think I have anything else to add. There are other ways of doing stratification. There are something called post-stratification, and there is, for Brownian motions, you can look up something called terminal stratification. But but I will not touch on those subjects since I hope this gives you an idea of how this works. So now I will continue to Python, where I will simulate, show you that this variance reduction actually works. So see you over in Python. Okay, here I'm back. I will now show you that this actually gives a reduction in variance compared to just using crude Monte Carlo. So I have created this file where I've written some code, and I will just go through it piecewise. So first of all, I import two packages that I'm going to need, the NumPy package and the NumPy random library. These libraries give some useful functions. I define a function which I call crude Monte Carlo. This is where I perform n simulations. Okay. So what I do here in crude Monte Carlo, I take an x, which is a vector consisting of 1,000 realizations of a standard uniform. Then I calculate the sample mean, and I add this to my out. So if I simply want to estimate this mean, I can run crude Monte Carlo 1. NumPy is not defined. Okay, let me run everything instead. Crude Monte Carlo 1. This gives me an estimate of something very close to the real mean, which is 0.5. But I can enter any value in here. I can, for example, write 10. Then I get 10 estimates. And we can see that all of these are very close to 0.5. But this is using crude Monte Carlo. Now I do the same for stratification, or using stratification. So here, instead of simply simulating x from a standard uniform, I use my example from before. So I sample some of them within x1, some within x2, some within x3, and I use proportional allocation. You see that up here I simulate 1,000 in total. Here I simulate 200 within the first interval, because there is 20% chance of being inside this interval, and 700 and 100, and you can see this sums to 1,000. Then I estimate the mean by taking the mean of the first, multiplying that by 0.2, then taking the mean of the next strata, multiplying that by 0.7, and then taking the mean of the third strata, or the outcomes from the third strata, and multiplying that by 0.1. And then once again, my out is simply a vector consisting of n different estimates. So if I run this one, we will see that if I just take 3 of these are also very close to 0.5. Now, what I do next is I estimate. Let me just write this out. I'll do that in a second. So I create 10,000 estimates using both methods. So in total, I have 10,000 times 1,000 simulations. So this is 10 million simulations using each of these. But Python is a very fast programming language, so this takes almost no time. Then I take the mean of my estimates, just to show you that that is extremely close to 0.5. And you can see this is very close to 0.5, and this is even closer to 0.5. But if we look at the variances of my estimates, then using stratified Monte Carlo, I have a very low variance here, but this is just an estimate, and it's based on 10,000 of these. Yeah, so I should, if I actually wanted to see what I want, I should probably write something like this. Then this is my estimate of the variance of the mean estimator. But this is not really important. What is important is that if I try to look at the variance of the stratified Monte Carlo divided by the variance of the crude Monte Carlo, then I should see that this is considerably lower than 1, because this variance should be a lot smaller than this variance. So if I try, and NP var simply calculates the sample variance. So if I consider this, well, I can see it's 0.36 or 0.356. And what this means is that this stratified variance, or this stratified estimator, has a variance that is only 35% of the variance of the crude Monte Carlo. And this is only approximative, because this is, of course, the sample variance. But this is the whole point of this method, that I can reduce the variance by 65%. And, well, these two functions, they're not really, it's not that much harder to simply do this. In fact, I could probably increase this even more if I just write 0.5 here, and then I change this again, random uniform 0.5 up to 0.9, then this should be 400, and this should be 300, and then here I should, I don't remember how I do this, plus the mean of x4 times 0.4, and change this to 3. So what I did is I created an extra strata. So if I run all of this code, and I then run this stratified again, then this should be even better. I really hope it is. Yeah, so we can see that just by creating this extra strata, my variance is now only 1/10 of the crude Monte Carlo variance. Yeah, so hopefully you found this interesting, because this is all I wanted to simulate. I could continue creating more and more stratas, as long as I remembered to keep this above like 100 for the central limit theorem to work. So yeah. Thank you very much for watching this video. I hope you got an understanding of how this stratification method works, and that you can use it in the future. If you enjoyed this video, please do consider liking and subscribing. And if there is some subject you would like to see covered, which is within the realm of probability theory or statistics or Monte Carlo simulation, please let me know in the comments. And also, if you have any ideas as to what I could do better to improve the quality of the videos I create, please leave a comment where you tell me what to do. I am very new at this, and I would very much like some feedback, because I'm sure there are a lot of things I could do better. Other than that, I wish you a nice day or evening or whatever the time is wherever you are, and I hope that you will be watching some of my future videos. So yeah, that's that.